In this video, we're going to talk about what an inner product space is. So our overarching goal is we want to find a way to generalize the dot product that we talked about in Rn. So sometimes the dot product, we refer to this as the standard inner product. The standard inner product. Okay, so we want to generalize this notion of the dot product that we talked about in Rn so that we can define terms like length, orthogonality, and projections in abstract vector spaces. So not just Rn, but more abstract vector spaces. So let's define this thing called the inner product. Okay, so the inner product on a vector space V is a function that satisfies the following axioms. So it needs to do this for all vectors u, v, and w that are in the vector space V. So looking at these, there's four axioms here. These axioms may look kind of similar because we've actually stated all of these axioms as properties that the dot product in Rn satisfied. So let me talk about some notation. So for the inner product, the notation that we use is we write these hard brackets like this. And this is notation for the inner product. For the inner product. Whereas for the dot product, our notation was we wrote like a dot, and then we wrote the two vectors on either side of the dot. Okay, so when we see something like bracket u comma v bracket, that means the inner product of u and v. So for example, the first property, which is called symmetry, says that if you take the inner product of u and v, that's the same thing as taking the inner product of v and then u. So the order in which you do the inner product shouldn't matter. So properties 2 and 3 are about linearity. Property 4 says that if you take the inner product of a vector and itself, that should always be greater than or equal to 0. And moreover, the inner product of a vector and itself is equal to 0 if and only if the vector is 0. All right. So one important thing that I want to note about the inner product and what it takes in and what it gives us out. So the input is two vectors. Two vectors. Or more generally, it's just two elements in my vector space. So we could be talking about two polynomials, for example, as the inputs. And the output, just like with the dot product, is going to be a real number. So the inner product will input two vectors and it'll output a real number. All right, so let's give another definition now of what an inner product space is. So an inner product space is just a fancy way of saying it's a vector space put together with an inner product, with a function that satisfies those four properties that we saw above. So for example, the simplest one that we can write at this point is if our vector space is Rn, we can define the inner product to be just the dot product of u dotted with v. So this is an inner product space because the dot product satisfies the four axioms above. And we had seen that in a previous section in this chapter. So next, let's look at an example. So here is our first example. So let's let V, our vector space, be P1. So this is all polynomials of degree at most 1. And I want to identify which of the following are inner products on P1. Okay, so because we're talking about polynomials of degree at most 1, our polynomials will have this form. We'll have some constant term, a0 plus a1t. So a1 being some other real number, and then t being our variable. So part A says that when we take the inner product of p and q, what that outputs is p of 0 times q of 1 minus p of 1 times q of 0. And then part B is kind of similar looking, except we have a plus, and then a couple of the terms are sort of switched. So I have the 0 terms in the front, p0 times q0, and then after that I have plus p1 q1. Okay, so which of these are inner products if any, and then which are not. So it turns out that part A is not an inner product. This is not an inner product. So let's talk about why. So before we do, I want to make a note that if we want to show something is not an inner product, we just need to show that one axiom fails. That one axiom fails to hold. Okay, so to get a feel for, well, which axiom that might be, initially we might not be too sure. So let's just begin with the first axiom. So the first axiom says, well, what happens if you look at PQ, P inner product Q written in this way, and then what happens if you do it in the reverse order? So the reverse order, let me write that in green, so Q inner product with P. Okay, so if we do P inner product with Q in this order, we'll get P0 times Q1 minus P1 times Q0. So this formula for the inner product that we had. When we do it in the reverse order, now we have to switch the roles of the Q and the P. So instead of beginning with P of 0, we begin with Q of 0. And then instead of Q of 1, we'd have P of 1. And then continuing in this way, we'd have minus Q of 1 times P of 0. So now looking at these two things, so looking at this thing in blue that I have, looking at this thing in green that we have, these aren't the same. In fact, in general, their signs are exactly opposite. So these two things are exactly opposite. So in general, they're not going to be the same. Generally, these are not equal. These are not equal. So this first axiom fails. So symmetry, the symmetry axiom fails. So this is not an inner product. One of the things that tips me off that this may not have been an inner product just by looking at it is, often when we see expressions with a minus sign like this has, we can sometimes, utilize certain axioms to show that things are not going to be the same. And that's what we did here. So for part B, it turns out that this is an inner product. So this is an inner product. So axioms 1 through 3 are easy to check. In general, that's the case. In general, when something is an inner product, axioms 1 through 3 usually are going to be easier to check. So let's talk about axiom 4, because I think that's the more interesting one here. That's the most difficult to show, but even here it's not too bad. So for axiom 4, that says, well, if you take the inner product of something and itself, well, what would we get? So if we had P and then P, we'd get P of 0 squared plus P of 1 squared. So if we take the sum of two squares, that's definitely greater than or equal to 0. So that's one part of it. That part holds. But the other part is, well, what happens if this whole thing equals 0? So if P of 0 squared plus P of 1 squared equaled 0, the only way for that to be true is if both of these terms, the P of 0 and the P of 1, if both of them equaled 0. That's the only way for this to be true. So if we were to draw a picture of this on a graph here, so I'm going to draw my axes. And at this point, I know that when I plug 0 into my function, I get out 0. So let's say this is where x is 0. And when I plug 1 into my function, I also get out 0. But we're talking about a polynomial in P1. So this is a line. So we need to be drawing a line that goes through these 2 points. That line has to just be the 0 polynomial. So the only possible line here is P of t equals 0. And that's what we wanted to show. That was the second part of this. We wanted to show that P inner product with P equals 0 if and only if P, my element, is 0. In this case, it was a 0 polynomial. That checks off axiom 4. We've shown it. So I want to end this video by now. Let's actually do an example where we find the inner product of two things. All right, so for example, in the inner product that we just defined in part B, so in this inner product in part B, let's suppose that P of t was the polynomial 2 minus t, and Q of t was the polynomial 1 plus 4t. All right, let's separate this part off. It's a little bit easier to read. All right, so now let's take the inner product of P and Q. So using the formula, this should be P of 0 times Q of 0 plus P of 1 times Q of 1. So let's just evaluate what that is. So P of 0 is, I get 2 minus 0, which is 2. Q of 0 is 1. P of 1, 2 minus 1, so that's 1. And then Q of 1, 1 plus 4, that's 5. So overall, we have 2 plus 5, which is 7. All right, so that's what the inner product of these two polynomials is. It's 7. All right. So I want to end this video now by stating two nice theorems about inner products. So the first theorem is what's called the Cauchy-Schwarz inequality. And this says that if you take the inner product of two vectors, and then you take the absolute value of that, right? Because an inner product just outputs a real number. It could be positive, it could be negative, it could be 0. So when you take the absolute value of that, that will be less than or equal to the length of u times the length of v. And the other theorem is the triangle inequality. The triangle inequality, so I'm going to explain what this is saying visually. So let's say I have a vector here, and I'll call this vector u. And then I'm going to add to u a vector v. So I'm going to line this up sort of like tip to tail. So the vector v, I'm sort of going to start at where u's tip is. Okay, and this is going to be my vector v. So when we add these two vectors together, when we add them, ooh, did I switch the color? Okay, now I think it should be. When I add them, we draw in this vector. So this is u plus v. So what this theorem says is if we look at the lengths of these, so if I look at the length of u plus v, and if I look at the length of u and v, well, the length of u plus v is less than or equal to the length of u added to the length of v. So conceptually, the reason why that's happening is when you take the length of u plus v, you're going in a straight line path from one point to another point. And then when you add up the lengths of u and v together, you're traversing, from the same starting point to the same end point, but you're not necessarily going in a straight path. You might be going in sort of an angle. And the reason why this is called the triangle inequality is graphically it shows up in a triangle like this. So in the next video, we'll discuss how to generalize length, orthogonality, and projections when we're talking about inner product spaces.